Okay, guys, what we're going to be working on today is just some of the examples from the homework. I'm going to be focusing on three problems I don't think I did in class, so you can see how to do more of the ones from the homework that maybe you hadn't seen already. So there's the dad joke. If you want to read it, pause it. I hope you enjoy it. And first problem we're going to be looking at is the diving board problem. Okay, so let's bring up my pen here. and let's start doing it here. A 50-kilogram box is placed 2.45 meters from the fulcrum, supporting a 4-meter long diving board. Okay, so this is a 50-kilogram box and is placed 2.45 meters from the fulcrum. This is a fulcrum, okay, guys? This is the thing that kind of holds it up. It's 2.45 meters. And when they write that, they mean 2.45 meters to the center of mass of this object. So it's really probably more accurate to draw like that distance. Okay, from the fulcrum supporting a 4-meter long diving board. Okay, so the entire diving board is 4 meters, and we can just say that the center of mass of the diving board then is at 2 meters. Yeah. To the left side of the board is bolted down as shown. The bolt is 80 centimeters from the fulcrum. Okay, so the bolt right here looks like it's 0.8 meters. Okay, from the fulcrum, and 0.2, so it was 20 centimeters from the left of the board. So this right here is 0.2 meters. Okay. The mass of the diving board is 10 kilograms. Okay, so the whole diving board is 10 kilograms. Find the full force that the fulcrum exerts on the board. So basically, you're trying to look at the upward force that this thing applies onto the board. Okay, so remember we're talking about torques, so it'll be the torques in the clockwise direction should be equal to the torques in the counterclockwise direction, and that's why it's at equilibrium here. Now my pivot point is going to be right here. The pivot point is going to be the bolt, okay? And because that's where it would fall down, and we're trying to look for the force acting upwards. So in a clockwise direction would be all the stuff going like this. So you got the box so a torque from the box plus a torque from the diving board. Okay, so I'll put diving board as dB, should be equal to the stuff in the counterclockwise direction, the stuff going the other way, which is just going to be the fulcrum. So the torque from the fulcrum. Okay, the torque from the box. Remember, that is force times radius on each one of these, right? The force would be, okay, force is going to be the weight of it. So 50 times 9.8. That's the force it has times the radius, so the distance it is from the pivot point, which is right here. Now, to figure that out, what I would say is it's 2.45 from the fulcrum to the box, and then 0.8 from the fulcrum to the pivot point. So to get that, what I'm going to do is 2.45 plus 0.8, because that'll give me to the pivot point. Okay, so that's the torque of the box. Plus, let's do the torque of the diving board. Okay, so the diving board is going to be the force, so it's going to be mass times acceleration. So the mass of it is 10 times 9.8 times the distance from the pivot point. Okay, so remember the force, the mass of the diving board is at the center, so at 2 meters, right? So I think what a lot of people would do is probably put 2 right here, but remember the pivot point is 0.2 meters away from the start of the diving board. So the distance from the pivot point to the center of the diving board would be 2 minus 0.2. So like that. It's going to be equal to the torque of the fulcrum, which would be the full force that the fulcrum has, yeah, times the distance from the pivot point, which the distance from the pivot point is 0.8 is what it said. So times 0.8. And then we just need to solve for that force from the fulcrum. Guys, if I exit out of this PowerPoint, it deletes everything I wrote on here. So I am going to do my calculations on a calculator, and I will just write what numbers I get here, so you can check if you're getting the same thing. Okay. So I'm doing 50 times 9.8 times 2.45 plus 0.8. Okay, so on that first torque from the box, I'm getting 1,592.5 plus, okay, it's going to be 10 times 9.8 times 2 minus 0.2. That would give me 176.4 equals the force of the fulcrum times 0.8. Okay, so I'm just going to add those together and divide by 0.8, and I'll get my answer. Okay, so that comes out to that plus that. So it's going to be 1,768.9 is equal to the force of the fulcrum times 0.8. So I'm just going to divide by 0.8, and I'll get the force of the fulcrum. So that divided by 0.8 would be 2,211. So 2,211 newtons. Okay, well, I only got one of these that is close to that, and that's what it would be. Now, the reason why it's not exactly is because they are doing significant figures, which would keep 3 digits, and that's why you're seeing the 221 and not the extra 1 there. Okay, so that's how you do that problem. Now let's go on to another one. This is the kid on the diving board. And I don't think you can see what's behind there because I think my video is over it. So look at it on your paper, and I can actually see it though. So I'll read it to you guys. Students are doing an experiment near an empty pool. The student has a mass of 40 kilograms. Okay, let me get my pen. Okay, so this kid weighs 40 kilograms, and is standing on the board at the end of the board, and the board hangs over the pool as shown. The board is of uniform density and has a length of L as positioned such that the pivot point is L over 3. Okay, so this is our pivot point right here from the end of the board. The board is just above, about to tip over into the pool. How far from the pivot point must the 60 kilogram student stand so that the board is just about to tip over? Okay, so there's a couple ways to do this one here. How about I show you how to do it mathematically, and then I'll show you how to do it kind of logically. Okay, mathematically, what I would assume you're probably thinking is you would have, okay, so like with this, you would work with this first set. So you'd have the force, the torques of the clockwise equal to the torques of the counterclockwise, right? Okay, the torques of the clockwise, this direction would only be the force of the board. So however much the board weighs, which it doesn't tell us, yeah? So just, I'll say the board weighs m times g times the distance from the pivot point. Now the pivot point, now remember the board's mass is at L over 2, somewhere over here, right? And the distance from the pivot point would be L over 2 minus L over 3. And that'll give us our distance from the pivot point, yeah? And then should be equal to the counterclockwise, which would only be the mass of the boy, which would be 40 times 9.8 times the distance he is away, which is L over 3. Now what we want to do is we want to see where this board would have to be if a 60 kilogram kid was standing on it instead of a 40 kilogram kid, right? Well, we know that it needs to equal the same thing. So what I'm going to do is I'm just going to ignore this side of the formula, and I'm going to say I want this to be when a 60 kilogram kid is there. Because both of these sides are equal, right? I don't know anything on this side. So I just want to ignore that side because I don't know anything over there. So I'm just going to focus on this side, and I'm going to set it equal as if a 60 kilogram kid was on it instead. So it would be 60 times 9.8 times whatever distance away it is, which I'm going to be looking for. And then you would just go about solving for x. So you would divide by 9.8, canceling them from each side. Yeah, and you'd be left with 40 times L over 3 equals 60 times x. We divide by 60, leaving us with 40 times L over 3 divided by 60 is equal to x. And there's our answer. We just need to simplify it so it's the same as on the answer choices. So the zeros would cancel, and that would leave you with the 4L over 3 over 6. And I'm going to put this over 1 so it becomes a fraction. And I can do the sandwich method. So that'll be my new numerator, 4L divided by 6 times 3 would be 18. And that can simplify by 2, making it 2L over 9. And that is where your kid would be standing. Now, one way to do this logically, and you can do this on a lot of the AP questions, is you know that if the kid is 60 kilograms, that means that you can move the board this way, and he's going to be able to hold it more down than the 40 kilogram child, right? So you would have wanted to find anything that was less than L over 3. And if you look at all the answer choices, which I didn't put on here, if you look at all the answer choices, only one of them is less than L over 3, and it's the 2L over 9. All the other answer choices would make the board move this direction, which, doesn't make sense. If you put a larger child on the board, you would be able to put more of the board on the other side of the pivot point, because it would balance out more, right? So there's two ways to do it: the mathematical approach, which I did here, and logically thinking on how you would to find it. So if you can't think of how to do it mathematically, think about it logically and see if you can figure it out. Okay, let's do one more here. I got the cog here that turns. Okay, so let's see here. I got a bunch of forces acting on this double type of pulley here. A system of two wheels fixed to each other is free to rotate about a frictionless axis shown axis through the common center of the wheel and perpendicular to the page. Four forces are exerted tangentially to the rims of the wheels as shown above. The magnitude of the net torque on the system about the axis is. Okay, so we're just looking for the net torque. Okay, so basically the net torque, whoops, I forgot to grab my pen before I clicked. So the net torque is going to be, having some problems clicking on the pen here. Okay, there we go. Okay, so the net torque is just going to be add all the torques up and see what you come out to have, right? And remember, torque is just force times radius, right? We're not dealing with angles yet. So let's deal with the torques from the clockwise and add them with the torques from the counterclockwise. And when I say add, they're going to be in the opposite direction, so a better way of probably putting it is saying subtracting them. Yeah? So the torques in the clockwise will count as positives. So clockwise would mean we're going this direction. So this would be a clockwise motion. So 2F times the radius it has, which is 3R. Okay, so that's one of the torques going in the clockwise. Let's see what else is going in the clockwise. Okay, that one is going opposite. That one's going in the opposite direction. That one's going the opposite direction. So it looks like it's only that one that was going clockwise. All the others look like they're going in the other direction, the counterclockwise, right? Okay, so we're going to subtract those because those will be negatives. They're going in the wrong direction. They're not going clockwise. So let's deal with this one first. So it'll be force times the radius it has, which is 3R. Okay, and then let's deal with this one. That'll be another force. It's going to be negative as well. Times it's also 3R. Okay, and then the last one here will be force times the radius it has, which is 2R. Okay, let's just work this all out. 2 times 3 is going to be 6FR, minus, that one will be 3FR. If you notice, these are all going to be FRs here. So 3FR, and that one will be 2FR. Okay, since they all have like terms, which are FR, then we can just put them together. So 6 minus 3 would be 3, minus 3, so we get, wait, did I mess up on one of these? Because that one would cancel there. 6 would cancel with those two, making it 0, and all that would be left over would be the FRs. Okay, so it would be negative 2FR. The reason why I was a little confused there was I was looking at these and I didn't see negative 2 anywhere, right? But the key word here is the word magnitude. Remember, magnitude is only the number. So in this case, 2FR. Okay. If they want the negative on there, they might say magnitude and direction, or they might just ask for the net torque. When they specified the word magnitude of the net torque is when you should have caught on that it's only going to be the coefficient. It won't be the sign that's on there. So there's our answer there. It's 2FR, and those are the 3 problems.